Welcome back. For today, we're going to start chapter 9, Differential Equations. This lecture is going to be very short. It's going to just be an introduction to what is a differential equation and what are the solutions look like for a differential equation. So first, let's look at the definition. Differential equation is an equation that contains the unknown function and the derivative of that function. It could be one or more than one derivative. It could be the first derivative, second derivative, third derivative, and so on. So the differential equation contains the function, an unknown function, and its derivative. And the order of that differential equation is basically the highest derivative, is the order of the highest derivative. So for example, this is a differential equation assuming that y is a function of x. Then you have f prime x, the unknown function, x times f of x. So the function f of x is unknown. If we knew the function f of x, then we would know the derivative as well. So there is an equation that contains the first derivative and the unknown function. The unknown function y. It's not always in terms of x and y. Sometimes they write f prime, sometimes they write dy over dx, and so on. So this is a differential equation of order 1. Normally they say this is a first order differential equation. And here's another format of a differential equation. You have derivative of some function p with respect to variable t. So this is some function of t. So p prime of t is given and equals to some constant k multiplied by some function p, and 1 minus the function p divided by m. And again, m and k in this point are constant. We assume that the variable is t. The derivative is taken with respect to t, so we assume the function is a function of t. And this is what we will look for. We will look to figure out what is that function that satisfies this equation. And again, this is the first order of differential equation because it contains only the first derivative. That's the highest derivative. And here another example, differential equation. You have the function y equals to f of some x, and the derivative, in this case, the highest derivative is the second. So this is a second order differential equation. Okay. At the moment, we don't want to, this section, we're not going to focus on how to figure out the solutions. We want to know what are the solutions look like, and how do we check if a function is a solution to an equation. Just replace it in the equation. For example, here, if they give you a function y equal to x squared plus c, where c is a constant, remember when you do the integration there would be a constant c. So here that's a general form of a solution, because the solutions are coming out from an integration and the derivative of that constant is always 0. So there is a general form of the solution we will discuss later. But so let's say we want to check to see, the question is this function y equal to x squared plus c a solution to the equation y prime equal to xy? Is this a solution or not? How do we check it? If we need to find out what is y prime, because we need to replace it in the equation. So I'm going to find out what is y prime. Y prime would be the derivative, simply 2x. The constant derivative would be 0. So does that satisfy the equation? So if we replace it in the equation, what do we get is 2x equals to x times x squared plus c. And you notice that if you simplify this equation, you simply get 2x equals to x cubed plus cx. And the answer is, this is not a true statement. It's not an equality for every x. Not true for all x. If it is true for all x, then you would consider this as the solution. So the solution should satisfy the equation. Later on you will see the solution to this equation, but normally if you check a solution, you just figure out the derivatives and replace it in the equation. Okay, how about this one? Is this equation y equal to 1 plus c e to the power t divided by 1 minus c e to the power t? Is this a solution to this equation y prime equals 1/2 y squared minus 1? This is the first degree differential equation. It contains only the first derivative. So y is given. We just need to figure out what is y prime to see if it satisfies the equation. Y prime would be, you have to use the quotient rule. So here 1 minus c e to the power t squared. Derivative of the numerator would be c is a constant. Derivative of e to the t is e to the t. Multiply by 1 minus c e to the t minus derivative of denominator times the numerator, which is negative c e to the t. The constant derivative would be 0 times 1 plus c e to the t. This is just simple quotient rule. And if you simplify it a bit, maybe you notice that this minus minus becomes a plus. So you have c e to the t plus c e to the t, 1 minus, so you will end up with, if you distribute and simplify, you get 2c e to the t. These two terms are exactly the opposite of each other. One is positive, one negative. When you distribute, they will cancel out. And so here, I'll divide by 1 plus c e to the t squared. Okay, this is our y prime. Let's replace y prime into the equation, in this equation, as well as y into that equation, to see if it satisfies the equation. So what we get is 2c e to the t divided by 1 plus c e to the t squared equal 1 over 2 y squared. So what is y squared? Y squared would be 1 plus c e to the t divided by 1 minus c e to the t squared minus 1. Okay. So here, simplify the left side. Let's keep it as it is. 2c e to the t divided by 1 plus c e to the t squared. And on the right side, you would have 1/2. If you square inside the parentheses the numerator, I'm going to keep the denominator just because I see exactly the same thing on the other side. So what do you have? If you do common denominator first, you will get 1 minus c e to the t squared, 1 plus c e to the t squared, minus, instead of the negative 1, I can write 1 minus c e to the t squared divided by 1 minus c e to the t squared. This is instead of the 1. It's the same thing. I'm trying to do common denominator. So I can write them together and say this is minus that with the same denominator. And now if you simplify the numerator, the left hand side is still the same, 2c e to the power t divided by 1 plus c e to the power t squared equal 1/2. Okay, 1 minus c e to the power t squared. And if you simplify the numerator, if you square each parentheses and subtract from each other, what you would get is 4c e to the power t. I'm kind of skipping over the step, but you have to square this minus the square of this. You'll notice that there's only a negative difference between these two. So the square terms will cancel out and only the term that contains, okay, maybe I should write it above it. So here this would be 1 plus 2c e to the t plus c squared e to the t squared, or c squared e to the 2t. And this one is exactly the same thing. Instead of plus here in between, you would have minus 2c e to the t plus c squared e to the 2t. Or you can write it as e to the t squared. And when you subtract, these two cancel out. These will cancel out, and you get 2c e to the t minus 2c e to the t, which is the same as 4c e to the t. And you notice that these two can cancel out, and you'll get 2. What you have on the left side is exactly the same as what you have on the right side. So that means this is the solution to that equation. The answer would be yes, that is the solution. This satisfies the equation. Okay. Yeah, so in these examples that I showed you, you always have a constant c. And you notice that that constant c could be whatever, it still satisfies the equation. You can pick 1, 2, 3, and so on. That still satisfies the equation. But generally speaking, sometimes they provide you with an initial value. And that initial value is just to create a particular solution, not multiple solutions, not the general form. So they'll give you some information. They say y at a certain value, like a t naught, is equal to y naught. It may be confusing, the notation, but it means that the y at some x value is given. So here, let's look at this example. Find the solution to the differential equation y prime equal to 1/2 y squared minus 1. Find a solution to this equation which satisfies the initial value of y0 equal to 2. So this is given for example, at t0, y is given, it is 2. So this means if t is given 0, y is supposed to be 2. Or you can look at it at the point 0 and 2 is on the curve, which satisfies this equation. We already know the solution to this one. We don't know how to find it, but it's given in the last example. Here it was given. Y equal to, this is 1 plus c e to the power t divided by 1 minus c e to the power t. This is the solution to that equation. We showed that that is the solution. So assuming we know the solution as the form of 1 plus c e to the power t divided by 1 minus c e to the power t, then this condition, this boundary, the initial value condition, is just to figure out what is that constant c. So which means if you replace 0 for its t, y must be 2. So that means if I replace 2 for y and 0 for t, I should have an equality. And again, this solution, it's given from the last example. We haven't talked about how to find that solution yet. But then now we can find out what is c. If you simplify the numerator, you have 2 equals 1 plus c, the denominator is 1 minus c. You can cross multiply, put the denominator 1, and you get 2 minus, this is the same as 2 minus 2c equals 1 plus c, and c would be simply, what is c? C would be 3 1/3. Sorry. Yeah, 1/3. Solve that equation. So you see would be 1/3. So what is the solution to the differential equation with this initial condition? Instead of c, simply say y of t is basically 1 plus 1/3 e to the power t divided by 1 minus 1/3 e to the power t. This is a particular solution, not the general solution. Particular solution with this initial value given y0 equal to 2. Here's another example. First they ask you, is this the solution to the equation y prime equal to ty? And then if yes, then find the solution that satisfies this particular initial value boundary, initial value problem. Okay, so first let's check if it's the solution. What is y prime? Because we need to find the derivative. Y prime would be c e to the power t squared over 2 multiplied by chain rule by the derivative of the numerator, the exponent. T squared over 2 derivative, which you can simplify c e to the power t squared over 2 multiplied by 2t over 2, which is simply t. So if I want to write it better, it would be c t e to the power t squared over 2. Just the ordering, so we don't make a mistake. And now I replace this y prime into the given equation, as well as for y. So y prime, which is c t e to the power t squared over 2 equal t times, what was y? Y was given here, c e to the power t squared over 2. Are these two equal to each other? Left hand side and right hand side, are they equal to each other? This is c e to the power t squared, here is e to the power t squared times c, and you have a t multiplied by that, t multiplied by that. So the answer would be yes, it is the solution. And now if we know the solution, find out what is the particular solution with this initial value problem. So since we know that y must be c e to the power t squared over 2, and y of 0 is given 2, so if I replace 0 for t, y must be 2, and you'd have c e to the power 0 squared over 2, which is simply 0. So that tells me that I have y equal to 2 equal to c. If I find c, then I can say the particular solution would be y is 2 instead of c, e to the power t squared over 2. This is the particular solution that solves that initial value problem. Okay, every other example is very similar to these for this section. So our purpose is in the next section to discuss how to find these solutions, because not always the solutions are given, and it's not always so easy to find the solutions, but we're going to discuss the ones that we can at least figure out in the next section. Okay, so I'm going to stop here.